Good morning, everyone. My name is Mhanna, and I'm a research associate at the American University of Sharjah. Today, I will be presenting our research project entitled Comparison of Shear Behavior of Normal and Recycled Aggregates Beams Strengthened with Carbon Fiber Reinforced Polymer URAPs. The co-authors of the project are Professor Jamal Abdalla, myself, Professor Rami Hawileh, and students Sadi Ahmed, Omer, and Abdulkadeer. This is the outline of the presentation. I will start with an introduction about the topic, and then I will move on with the research significance, and then I will explain the experimental program, followed by the results and the discussion of results. Finally, I will be concluding the presentation. With more construction these days, there is more demand for aggregates. Construction and demolition waste usually account for approximately 25 to 30% of all the waste generated. It is noteworthy to mention that steel and concrete, which are the two primary conventional materials used in the construction, that require large amounts of energy. In order to address this issue, there is a need for greener alternatives to materials such as concrete. While there have been current approaches to solving this issue of the negative environmental impact in the construction industry. These include the use of materials from coal combustion products. In fact, the use of these materials activated by fly ash that are recently developed leaves virtually no carbon footprint on the environment. Another sustainable solution is to produce concrete using recycled aggregates. An alternative approach could be also to retrofit existing reinforced concrete structures instead of demolishing and building new structures. There are several advantages to use recycled aggregate concrete instead of normal aggregate concrete. First of all, keeping the concrete debris out of landfills saves the landfill space. Second, the use of old construction materials curbs the extraction of other natural resources. In addition, using recycled materials such as gravel reduces the need for gravel mining, which depletes the natural resources and creates waste. In addition to that, using recycled concrete as a base material for roadways reduces the pollution involved in trucking material. And finally, it reduces the greenhouse gas emissions and non-renewable energy consumption. As I mentioned earlier, another method to reduce the negative environmental impacts of the construction industry is to retrofit existing reinforced concrete structure. And one method that has deemed effective in strengthening of RC structures is conducted via bonding a fiber-reinforced polymer composite onto the concrete surfaces. Usually, using FRPs in strengthening of RC structures is effective in enhancing the strength and the performance of the structure. There are several advantages of FRPs as opposed to other conventional strengthening methods such as steel plating, for example. These include high strength-to-weight ratios, versatility. FRPs are non-corrosive in nature, therefore they're durable, and finally they reduce the harm on the environment while maintaining high level of strength in the concrete. Moving on to the research significance. In general, shear failures are catastrophic and brittle. Therefore, the use of FRP materials could be essential to improve the shear capacity of the beams. Numerous research studies were conducted to study the strength enhancement and performance of reinforced concrete beams strengthened in shear with FRP. However, there is a gap in the literature on the effect of strengthening RC beams composed of recycled aggregates with FRP laminates. Therefore, the study aims at reducing the environmental impact by using recycled aggregate concrete while maintaining the shear strength parameter using FRP composites. As for the experimental program, the cross-sectional dimensions of the beams were 150 mm in width and 260 mm in height, and the beam spanned for 2 meters in length. The beams were reinforced in flexure with 2 number 12 bars in the tension zone and 2 number 8 bars in the compression zones. In addition, the effective depth was 216 mm. You can see here from the figure that the beams did not include internal shear reinforcement except at the location of the supports and the center to hold the flexure bars in place and to prevent premature failures at this location. A total of 4 reinforced concrete beams were tested in the study. 2 specimens were cast with normal aggregate concrete and 2 specimens were cast with recycled aggregate concrete. One of each specimen was left unstrengthened to act as a control specimen. And then the other 2 were strengthened with CFRP URAPs, as you can see here. This is the strengthening details of the beam. The URAPs had width of 100 mm and spanned along the length of the beam between the supports. The URAPs were also placed 50 mm from the top of the beam, as you can see here. In addition to prevent flexural failure, the beams were reinforced in the tension zone with a single layer of CFRP sheets of dimensions 1,850 mm by 150 mm. Moving on to the material properties. First, the concrete. Two self-consolidating concrete mixes were prepared in this study in a ready-mix plant. One mix contained 100% natural aggregates and the other mix contained 100% recycled aggregates. Two sizes of coarse aggregates were saved, which are 0 to 5 mm and 10 to 20 mm. The fine aggregates were natural sand from the river. The first table shows the physical and mechanical properties of the recycled aggregates used in the study. And we should also note that all the tested properties comply with the accepted values according to each standard tested. The mixture proportions of the fresh concrete mixes are provided in Table 2. Owing to the high absorption of recycled aggregate concrete, there is an additional amount of water that was added to the mix to ensure workability. This was like 35 liters per meter cube. This amount was calculated based on the water absorption and the predetermined absorption capacity of the recycled aggregate concrete at 24 hours. Concrete cylinders were cast and cured with the beams to determine the compressive strength of concrete. The cylinders were tested after 28 days, and the average obtained compressive strength was 37 megapascal for the normal aggregate concrete mix and 36 megapascal for the recycled aggregate concrete mix. As for the steel, tensile tests were conducted on the 8 and 12 mm rebars, and the obtained average yield strength was 550 megapascal with an elastic modulus of 200 gigapascal. The table here shows the material properties of the CFRP and epoxy used in the study. The CFRP laminates had a design thickness of 0.5 mm with 83 gigapascal elastic modulus and 1,492 ultimate tensile strength. The beam specimens were simply supported and tested under two-point loading tests. A universal testing machine was used to apply the load at a displacement-controlled rate of 1 mm per minute. The load was applied at the center on a spreader beam that divided the load into two equal parts, and the shear span and overhang lengths were 615 and 75 millimeters. In addition, strain gauges were placed onto the center of the U-wraps on both sides of the beam to monitor the strain in the CFRP U-wraps. In addition, one strain gauge was mounted onto the concrete to monitor the strain in the concrete. In addition, one LVDT was placed mid-span at the bottom of the beam to measure the deflection of the beam. Moving on to the results and discussion, starting with the failure modes. The first picture here shows the typical failure mode for the normal aggregate concrete and recycled aggregate concrete. As seen here, the beams failed by typical shear failure by the formation of a critical shear crack at an angle of 45 degrees from the horizontal. The major shear crack propagated from the supports up to the loading point, as you can see in the figure. Also, minor shear cracks were formed in the shear span. On the other hand, the specimens NU and RU primarily failed by the debonding of the U-wraps, as you can see in these two figures. The failure in the strengthened specimens was initiated by the formation of shear cracks, and as the load increased, the cracks widened and the bond between the U-wraps and concrete was lost, which consequently resulted in the debonding of the U-wrapped laminates. It was observed that the U-wraps that debonded from the concrete were the ones that intersected the critical shear crack. Mainly the middle three U-wraps were the ones that debonded. Moving on to the summary of test results, this table shows the summary in terms of the maximum attained load, which is Pn, maximum shear force, calculated by statics as Pn over 2, the midspan deflection at maximum shear force, the maximum strain attained in CFRP laminates, the shear in the concrete, and the FRP contribution to shear capacity, which is B sub F, and the observed failure modes. It should be noted that due to the absence of steel stirrups in the beams, the shear capacity of NC and RC beams were considered the concrete contribution to shear capacity for the U-wrapped specimens, and consequently the FRP contribution to shear capacity was calculated by subtracting Vn from V sub C. You can see here that the strengthened specimens with CFRPU wraps, NU and RU, perform superior to the unstrengthened beam despite the aggregate type. The percentage increase in the shear strength is higher in RU compared to NU, with a 60% increase in specimen RU and 36% increase in specimen NU. The maximum strain attained in CFRP laminate before failure for both the U-wrapped specimens were comparable, as both specimens attained very close load capacities. Moving on to the shear force deflection graphs, we can clearly see here that prior cracking, all specimens had similar stiffness. However, post-cracking, the advantage of the U-wraps was evident in enhancing the stiffness of the beams. We can also see that without strengthening, the behavior of NC and RC beams was almost identical, with the shear force deflection curves almost overlapping. The inclusion of the U-wraps also resulted in similar shear strength, as you can see here in specimen RU and NU. However, the specimen NU had better deformation capacity than specimen RU and failed at higher deflection. The shear strength of the tested beams was predicted using ACI 318 for the unstrengthened beams and ACI 442R for the strengthened beams. So you can see here from the table, this is the shear capacity, experimental shear capacity, and this is the calculated predicted shear capacity, and this is the ratio of the experimental to predicted. As you can see from the table, the shear strength predictions of the control specimens were underestimated and conservative, with the ratio of experimental to predicted to be greater than 1. On the other hand, the ACI provisions provided unsafe predictions for the U-wrapped specimens NU and RU, with the ratio less than 1. Despite that, the results are deemed reasonable considering that all reduction factors were not included in the analysis. And we can say that in general, both sets of beams were closely predicted by the ACI provisions, and we can safely implement the ACI provisions to design NAC and RAC beams. In conclusion, based on the experimental results, the following conclusions were drawn. Strengthening of normal aggregate and recycled aggregate concrete beams with CFRPU wrap significantly enhanced the shear capacity by 36 and 60%. In addition, the recycled aggregate beams provided similar shear capacity to the normal aggregate beams with a maximum percentage difference of 5%. The use of recycled aggregate concrete contributes to a positive impact on the environment without compromising the strength. And finally, design provisions of the ACI could be effectively used to predict the shear capacity of unstrengthened and strengthened normal aggregate and recycled aggregate beams. Thank you for listening. If you have any questions, please feel free to ask.